Hey, grasshoppers. So today we are going to actually dive into quadratics, okay? Our first lesson in this unit was more or less just a review of factoring, making sure we're all on the same page before we get into this newer concept, okay? So the purpose of today's lesson is a couple of things. Number one, we want to introduce what a quadratic is, what a parabola is, what that shape means, okay? And then we want to start our journey along different forms of writing a quadratic. So you'll recall in 10C, we spent probably a month on writing equations of lines, okay? And we had three different, pardon me, we had three different ways to do that. We could write the equation of a line in standard form. We could write the equation of a line in slope y-intercept form. We could write the equation of the line in general form. We could write the equation of the line in slope point form, okay? There's actually four different ways we could write that. Now, I'm giving you information there, and as I'm thinking it through, we never talked about standard form. It is a thing, but don't worry about standard form there. But we did do the other three, okay? So the next few lessons are going to be sort of like that, okay? We're going to introduce the concept of a quadratic today, and then over the course of a few days, a few lessons together, we will deal with all the different forms, or some of the different forms that we can write a quadratic in, okay? Okay, so a quadratic relation or equation is in standard form when it looks like this: y equals ax squared plus bx plus c, where a, b, and c are all real numbers, okay? The shape that it produces is called a parabola, okay? Now, I'm just going to hide myself for a second, just so those of you who don't have the book at home can see those words, okay? And if you don't have the book at home, I'm going to show you a picture of this in 1 second. The following are important for important parts of the quadratic graph. So first of all, we have a vertex. The vertex is the minimum or the lowest point, or the maximum or the highest point on the graph. This is where the graph changes direction, okay? So the shape itself, and I'm going to show you this in a second, but I'll just draw one so that we can talk about it as we go. Okay, so right here would be the vertex. Okay, so in this one, it's the lowest point, but you can imagine if my graph had looked like this, remember the shape itself is called a parabola. Okay, the equation is a quadratic equation. So here I would have a top for my vertex, so I would have a maximum there, okay? The equation of the axis of symmetry, in order to be symmetrical, it means that I can flip myself over on the other side and I'm the exact same thing, right? So with parabolas, there is a line of symmetry. There is a line that you could draw down the middle and it would exactly flip or exactly cut the shape into reflective parts of one another. So that would be right here. Anytime in math that we draw a line that we talk about, but it's not actually part of the equation, it should be a dotted line. Just take note that I drew that as a dotted line, okay? And then this would be x equals whatever value x is at the vertex, okay? That would be the equation. So it's an imaginary line that cuts the graph in half vertically. This line always goes through the vertex. Then we have x-intercepts. That's the point where it crosses the x-axis. That shouldn't be really all that familiar to you, or unfamiliar to you, because we talked about that in 10C. We have a y-intercept as well, which is where it hits the y-axis. I'll just hide myself there for 1 sec in case you don't have those words at home. Okay, so in this one, the y-intercept would be right here. So we've got x-intercepts, and your y-intercept down there. Okay, then we'll also be talking about the domain and range of these graphs, just like we did in 10C. The domain is all the possible x values, the range is all the possible y values. You will have to be specific in how you write those, okay? We need proper set notation for domain and range, or interval notation if you know how to do that. We won't focus too much on interval notation in 20-2, but it is a thing, and if you want to do it that way, that's totally fine. Okay, and so if I showed you a graph of the quadratic, I'm just going to hide myself for a second. We see all of these important points, just like I had drawn on the board there. So the axis of symmetry is that vertical line, y-intercept where it hits the y-axis, x-intercepts where it hits the x-axis, the vertex is where it changes direction. Okay, the domain of all quadratics will be x's, remember the reals, because they move left and right forever. And then the range of all quadratics just depends on whether the graph is opening up or down. If the graph is opening up, it'll be greater than whatever the bottom is. And if the graph is opening down, it'll be less than whatever the bottom is. Okay, or sorry, less than whatever the top is. Okay. So we're going to play a bit on our graphing calculators. If you have a graphing calculator, awesome. If you don't, you should pause me and go get it. Your job is to figure out what happens to A, B, and C as we move them to different spots. Okay, so I am going to walk you through graphing one or two of these just to give you a review of your graphing calculator. After that, I'll just get you to pause and do it yourself to make sure you are okay graphing things on graphing calculators. So we're going to graph y equals x squared minus 2x minus 3 and y equals negative x squared minus 2x minus 3. Now, what did we do? First of all, well, we made that a value. Remember, let me just hide myself here for a second. And I just need some ink on. So this number right here is the a value. This number here is the b value. And this number here is the c value. This number here is the a value. This number here is the b value. And this number here is the c value. Okay, so what we're doing with these two equations is we're just playing around with the a value. We're making one of them positive and one of them negative. Okay, so now I'm going to switch over to my graphing calculator. If you just give me 1 second, I have to find it here. Okay. Okay, so I'm going to do this on a Casio. Those of you who have Casios, you would press menu and you'd be looking at something similar to mine. You want to go into your graphing feature, which is option 5. Okay, if you are a TI following along, you want to press y equals button, which is just up in this top left-hand corner here. It's around where my F1 button is. Okay. All right, so we're going to type in those equations, which were x squared minus 2x. So your variable button is right here. On a TI, your variable button is over here. It'll say x theta tn, like the Casio says x theta t. So I've got x and then squared. We're going to minus 2x. And we're going to minus 3. Okay, now hit execute, and that will register the equation. On a TI, that's hit enter, and it will register the equation. Okay, and then in y2, we're going to go negative x squared. Make sure you do a negative sign there. Your calculator does differentiate between what a subtraction sign does and what a negative sign does. So make sure you start with that negative sign, and then subtract 2x. Don't go back to the negative sign there. It needs to be a subtraction sign now. And then subtract 3. Okay, and we're going to hit enter. Okay, now I want to make sure we're all looking at the same thing before we look at it. So we're going to go to our windows. So on a TI, you're just going to go shift window. And we're going to go back to a standard for a sec, just so we can start with the same drawing. So I want Casio kids to press F3. And then on a TI, you'd press zoom 6 and you'd get the same thing. Casio kids press enter, or sorry, exit, and then we're going to draw. Okay, so we all should be looking at the same thing now. What's the difference between the blue and the red? Well, the blue opens up, the red opens down. What was the difference in the equations? The blue had an a value that was positive, and the red had an a value that was negative. Okay. So let me just switch back to the PowerPoint slide now. Okay, so this is the equations that you should have had. And here's the picture that you should have gotten. I changed my window settings, so I got a little closer in there. Okay. And we see our axis of symmetry at x equals -1 here, our axis of symmetry at x equals 1 for the blue. I've added in my x-intercepts and I've added in my y-intercepts, okay? The direction said sketch the graphs and label the parts A through D. So that's what I've done. And that'll often say label the important parts, okay? The important parts, well, would always be your vertex and your intercepts, okay? Okay, so did the shape change? Did it become wider or narrower? The answer there is no. Did the y-intercept change? Well, let's look. The y-intercept's here for both of them. Nope, it didn't change. What main characteristic did change when the A value was changed? The graph opens up, down instead of up. So when A is positive, the graph will open up. When A is negative, the graph will open down, okay? So when A is positive, up. When A is negative, down. Okay, cool. Now we're gonna head to start playing around with the B value. So you'll notice I've given you 3 different equations this time. I've got -2 for a B value, I've got 0 for a B value, and I've got +2 for the B value. So I would like you to put all those in your calculator for me, okay? Pause me and then compare. I'm gonna show you the graphs here. Okay, this is what you should have gotten. So I have things color-coded. The blue is right here, and the red, and then the green. So same sort of questions. Did the shape change? So did it get wider or narrower? And the answer to that is no. Okay, I'll just hide my face here for 1 second so you can see that question. Okay, did the y-intercept change? No, they actually all have the same y-intercept. So what did change? What I want you to notice there is we are moving it left or right, okay? Moving the axis of symmetry left or right. So the axis of symmetry, the x value of the vertex, moved right or left, okay? So that's what the B value does. Let's add that into our conversation. When B is changed, the line of symmetry moves left or right, okay? Okay, now we're going to take a look at these 3 graphs. And what I want you to notice is I've kept A the same. I've kept B the same. This time I'm playing around with the C value. So in my blue graph, it'll be -3. In my red graph, it'll be -5. And in my green graph, it'll be +1. Okay. So go ahead and graph those and see what you got. Okay. So you should have a picture that looks like this. We'll go through those questions in a second, but what I want you to notice right off the bat, it looks like this thing is going up or down, okay? The shape of the graph isn't changing. It's not becoming wider or narrower. It's just being moved up or down. And is there anything that kind of compares to this -3 on the blue graph? Well, what I want you to notice is, look at what's at -3, the y-intercept. -5, look at what's at -5, the y-intercept. +1, hey, look at what's at +1, the y-intercept, okay? Okay, so we're gonna ask the same questions. Okay, I'm just gonna hide myself for a quick sec. Did the shape change wider or narrower? No. Did the y-intercept change? Yes. And then the main characteristic that changed when C changed was the graph moved up or down, causing the y-intercept to move to the C value. Okay, so the y-intercept moved to the C value. All right, awesome. So we'll add that to our little list here. The C value is the y-intercept of the graph. Now, that's also known as the constant term. Okay, I want you to write that down somewhere because that's important to your life. This is called the constant term. The constant term is the number by itself in any general form of an equation, okay? Okay, now, explain why this statement is true. Let's go back to that y equals ax squared plus bx plus c format, okay? For any quadratic in the form y equals ax squared plus bx plus c, the value of the y-intercept can be calculated by plugging 0 in for x. Why? Why is that possible? Well, take a look. Anytime I'm on the y-axis, all of these guys would have x values of 0 because they haven't moved left or right. So maybe this guy here might be 0, negative 3, and maybe this guy here might be 0, negative 2, and this guy here might be 0, negative 1, and this guy here might be 0, 1, and this guy here might be 0, 2. What I want you to notice is x is always 0 there because I have not moved left or right, okay? So if I haven't moved left or right, there's no other value for x that I can put there but 0. So that helps algebraically. And we've done things like this with lines last year. We plugged 0 in for one of them and solved for the other if we were looking for different intercepts. So we're going to do that into the y equals ax squared plus bx plus c equation. So I've written my equation, y equals ax squared plus bx plus c, but I've substituted x with 0. Well, what happens? A times 0 squared is just 0. B times 0 is 0. And we're left with c. So that's why the y-intercept in that form will always be the constant term, will always be the value of c, okay? Where the value, when we get into higher degrees, it'd be the value of the number by itself without a x, okay? All right, awesome. Hopefully this all makes sense. Hopefully you're having a little bit of a better understanding of what A, B, and C do, and that you're starting to understand what quadratics look like, how they always look like a parabola, and what the general shape of a parabola is, okay? If you are my kid at school, I've posted your homework here for you to work through. And as always, make sure you connect with me if you have any questions. Okay, you guys got this. Next up, we're going to look at a different form of a quadratic called factored form and some of the cool things that shows us, okay? But until then, happy mathing. Take care, guys.